Hey there, in this video we're going to look at how we can calculate a linear least squares fit. Here's the problem we're trying to solve. Let's say that we have a collection of data points and we suspect that they are following a line, that they're linear, and we want to figure out what is the equation of the line that best passes through those data points. So we are trying to fit the function y equals mx plus b to some collection of data that in our computer will store in an array. And the way we calculate this best fit is to minimize a quantity that's named chi-squared, where the squared is really part of its name. And chi-squared is defined as a summation from I equals 1 to n for n data points of yi minus f at xi divided by sigma I squared. And so the sigma I in here represents uncertainty, as in what is the estimated uncertainty point by point. And it matters if that uncertainty is different for different points, because we want points that are more certain be closer to the line, and points that are less certain should have very little effect on the shape of the line. So we are going to simplify our problem by assuming that all of the sigmas are identical. And if that's the case, it won't factor into our minimization problem. We can effectively create a new quantity that just doesn't have the sigma in it at all. The other terms in here are the yi and the f. So the yi is the actual data, and f at xi is our best guess for what function that data follows. So in this case, it would be a line for a linear least squares fit, mx plus b. There is such a thing as a nonlinear least squares fit, which is basically the same kind of technique for nonlinear functions. The advantage is we can actually do this problem by hand, and a lot of data is actually linear. So we're going to define a new quantity L, which is just like chi-squared but doesn't have the sigmas in it. We're going to minimize L. L is going to be a summation 1 to n of yi, and then we'll explicitly put in the function mxi plus b, and then we're going to square all those differences. And we're trying to minimize the square of those differences. If you're wondering why squared, because being above the line is the same as being below the line. And so squaring will take a negative number and make it positive. So the way we're going to minimize is we're going to take the partial derivative of L with respect to m and set it equal to 0, while also taking the partial derivative of L with respect to b and setting that equal to 0. So let's try this out by hand for just 3 points, just to get a feel for what happens as we run through the problem. And then we'll look at making our computer do this for the general case. So in our example here, we're going to have 3 points. -1, -2, 0, 0, and 1, 3. And if we make a plot of those points, we'll find that they don't quite all line up with each other, because that would be kind of boring if they did. So we've got a 0, 0, got a 1, 3, and then we have -1, -2. I guess I put that one down a little bit too far. Sort of like that. And so they don't quite line up with each other, and there's some kind of best fit line that like cuts through here. And we're trying to find that line. So L is going to be equal to, remember it's the summation yi minus mxi plus b quantity squared. So it's going to be equal to, we're just going to go point by point. So the first y that we have in here is going to be a -2. We're going to subtract -1 times m, so -m plus b, square that. Next term is my favorite because it's got lots of zeros in it. 0 minus 0 plus b squared. And then the last term is going to be 3 minus m plus b squared. Okay, let's simplify this a bit. We're going to have in here, I'm going to square each of these, so 4 plus m squared b squared, and then we have all the cross terms. So that would be a negative 2 times m times another 2, so negative 4m. And we're going to have a 4b, and then we'll have a negative 2mb. And then for the middle term, it's just a b squared. And for the last term, we're going to have 3 squared is 9, plus m squared, b squared, and then the cross terms, negative 6m minus 6b plus 2mb. Okay. I do notice that the mb terms will cancel out. And now simplify a bit. So the constants, I have a 9 and a, not 9 squared, a 9 and a 4 is a total of 13. I have a total of 2m squared. I've got 1, 2, 3 b squareds. Then for my m's, I've got a negative 4m and a negative 6m, gives me a total of negative 10m and a total of negative 2b. Okay, so now we can do those partial derivatives. Partial derivative with respect to m is going to give me 4m minus 10, and that's going to be set equal to 0. That tells me that m has to be 10 on 4, or 5/2. Partial of L with respect to b is going to be 6b minus 2. Set that equal to 0. Tells me that b has to be 1/3. Okay, so we've solved this one by hand, but you can imagine that running through this, or the steps that we followed here, could be programmed into a computer, and so you can make your computer do this for you and give you the one best fit line for a collection of data. I think what's really cool is, given some scattered data, there's always exactly one best fit line. That's why it's the best. It's not like there are best fit lines, there's just one. And in this case, putting it all together, our best fit line is 5/2 x plus 1/3. So I'm back in the notebook, and I wrote a comment here just to remind me of the points we did when we solved this problem by hand. So we fit the points -1, -2, 0, 0, and 1, 3. Now you can imagine running through that problem entirely symbolic. So instead of plugging in values like -1, we just have a value like a1. And working through it completely symbolic, we could write, when we were done, an equation that would tell us the slope and the intercept of that line. And we could repeat that exercise with a quadratic, with a cubic, with any kind of polynomial function. And although the math would be tedious, we could create then a single expression that tells us the coefficients that go along with that polynomial. So you can do this exactly with the least squares, the linear least squares fit. And that hard work has already been done for us. It's in NumPy, and the name of the function is Polyfit. So if we look at the documentation here, it's a least squares polynomial fit. And what we need to give to it is x values, y values, and the degree of the polynomial. We don't really need to worry about the other arguments here. So let's try it out. I need to create an array for the x values and an array for the y values. So my x values were -1, 0, and 1. And my y values were -2, 0, and 3. Now we could try a polyfit x, y, and if we're fitting a line, that would be a degree 1 polynomial. So what this is going to return then is a tuple of the coefficients. Let's check what order they come out at. So if we scroll down here, it returns this p here is an array, or for our purposes, we can use tuple unpacking for it, even if it's not technically a tuple. And it comes out here, coefficients highest power first. Okay, so if we're fitting the slope and the y-intercept to a line, the highest power coefficient would be the slope. That's the one that goes with the first power term, and then the y-intercept be the second. So that would be m and b if we're doing the form y equals mx plus b. And then let's print these out and see if it matched our result from before. So we're going to do here something like m equals m and b equals b. And we probably want to round this to some number of decimal places. Let's do like 2 decimal places. Yeah, let's see what we get. We get invalid syntax. Why? Oh, because for whatever reason I typed in a quote instead of a colon. And I forgot my quote at the end of the string. Oh, there's 2 of them. Not being helpful, Jupiter. Okay, there we go, 2.5 and 1/3. So Same thing, except it was faster than doing it by hand. And the nice thing here is, since this is a computer program, it coded in there already is the way to do any polynomial. So let's try doing something that's third order. We're going to need to make some data here, and then we'll fit it. So we're going to start here where our x data is going to come from a lin space. I'm thinking we're going to do third order cubic here. So let's go like -2 to 2. We'll do 100 data points in here. And then let's start with the answer, like what y actually is, and then we'll add some error to y. We'll add some random numbers to y so that we don't have an exactly perfect function to fit, because, you know, it's boring if it's exactly a cubic to begin with. So let's go with 2 times x cubed plus x squared minus 3x. And how about we'll have no constant term. Okay, so then the coefficients here are 2, 1, -3, and 0. And so hopefully that's what the polyfit will give us once we fit it. Now let's make this a little bit more interesting by adding in some error. We can get that with a random number. So we'll do, I'd like my error here to be numbers that are centered around 0. And so this is a good place to use a normal distribution. So from random we could do .normal or .randn. The difference here is randn is by default centered around 0 with a standard deviation of 1. Normal gives you control over the standard deviation and the mean. But I think that's fine. We'll do 100 of these. And let's make them a little bit smaller. So we'll multiply every number in here by 0.4. I think that would look good. We don't want it to be too noisy, because then it becomes harder and harder to fit, because then the data is less and less like the original cubic. But I think this should be a good compromise. And so then I just want to add the error term to y. And so this will add some scatter around it. Let's plot it just to see what this all looks like and make sure I didn't make it too noisy. So I'm going to make a figure here that's wider than normal. Let's go with 12 and 4. I think the default is 6 by 4. So we'll make this like twice as wide as normal. And then I'm going to plot x and y. And let's use dots for these. We'll do red dots. We'll represent our data. We'll do bigger dots. Period for little dots, O for bigger dots. And let's show it. Okay, so there's our function. Looks like that noise was a pretty good size, because it's kind of, I can still see that it's a cubic, but it's not exactly smooth anymore. It's got some random noise to it. Now we're going to try and fit a line to that using, or not a line, we're going to fit a polynomial to that using Polyfit. So we'll call our coefficients a, b, c, and d. And so ideally a, if we come up here, would be 2, and b would be 1, and so on. I'm going to polyfit x and y up to third order. And then let's print what we get for our answers. So that would be like a equals a, 2, we'll do 2 decimal places, and so on. Copy this. Okay, I don't need that space there. We'll do B, C, and D. Okay, let's just start with that and check. So A was supposed to be 2, and it's really close to 2. B was supposed to be 1. C was supposed to be -3, and D was supposed to be 0. So that's looking pretty good. So let's try drawing our best fit on top of our original graph. I'm going to copy the plotting code. And then in here, we want to plot our fit. So it'd be something like plot x versus the fit to our data, and we'll do like a solid line. We'll do like some kind of solid line, probably default to blue. Now for fit, since we know a, b, c, and d, we can just plug those here into our function. So we could do a times x cubed plus b times x squared plus c times x plus d. Okay, let's see what that looks like. So we've got our nice blue fit line here on top. Maybe do something like a black line just to make it show up a little bit better. So we can see that's a nice smooth function. Looks like it's a really good fit to the data. I mean, it better be, because we knew the original function in the first place. Like here, we already know what it's supposed to be. Now, ways this could go wrong would be like if you had your data and you fit the wrong order polynomial to it, like you tried to fit a second order polynomial to it. In that case, we'd only go out to C. You know, it would try its best. It's going to give you some coefficients. But when we actually get down to plotting the thing, you can see it's terrible. Like this is the very best quadratic that fits this cubic data, but it's still not a good fit. So the function's not going to save you from doing a bad fit in the first place. It has to actually have that underlying form. There is some human intervention needed here. But as long as the data is cubic and you fit a cubic to it, then you're in good shape. Another way this can go wrong is something called overfitting. So here, what if instead of doing like second order or third order, we went crazy and we did like 50th order? Of course, I don't want to print out all those coefficients. And so we need some better way to fit such a high order polynomial. We could just call this coefficients and just let it be an array of coefficients. Now we got a warning right away. Polyfit may be poorly conditioned. Like it's yelling at us like, what are you doing? But supposing we're stubborn, we ignore it. We're running some bigger script. We didn't even see this error message. Like what has happened now that we fit this 50th order polynomial? Well, to get a good sense of that, we're gonna have to do something different here with our fit function because I'm not patient enough to type out 50 coefficients. There is a shortcut for this built into NumPy. It's called Poly1D. We look at how Poly1D works. It's convenience here used to give us polynomials. So what we do is we give it an array-like of coefficients. Hey, that's exactly what we had returned up here from Polyfit. So we're going to put that in as the argument. What comes out is effectively the polynomial itself. So if I put my coefficients in here, and then I could do something like fit equals Poly1D. Now let's try plotting that. Oh, it got mad at me. Do I have something here the wrong size? 151. What did I just do wrong? Oh, I used this wrong. Sorry, my bad. So fit here is like a function. So we have to, let's give this a different name. Let's call this poly, and then fit calls poly. So again, just coming back to this, the way Poly1D works is it returns a function. It doesn't return an array, it returns a function, and then to get the array, I have to give that function an array x so it can calculate each value. This should work now. Okay, so what we can see is, is this a better fit? It connects more of the dots. The answer is no, this is a much worse fit. This is called overfitting. To your eye, it looks, it looks good, but the underlying data was it was a cubic. And so fitting a 50th order polynomial to it is not better, it's worse. If you think about why would you even fit a curve in the first place? It's because you have some kind of physics you're trying to study here. You've got some measurements and you're trying to fit some parameters that have some physical meaning. And there's a big difference between a system that's described with 3 parameters versus a system that's described with 50 parameters. If you create some kind of model and it needs 50 parameters, you probably have a pretty bad model. On the other hand, if your model only uses a few parameters, then it's more likely to be a good model where those parameters actually have some kind of physical meaning. So be careful about going too high order with your fits. You want to go as low order as still fits the data. Okay, so we'll stop there in this video. We looked at how we can use Polyfit. We looked at a helper method here that you usually don't need because this is more if you're lazy and you have too many coefficients. But the star of our show here is our Polyfit.